Hi there. It's Friday, October 11th, 2024. This is your lecture 12, your Thanksgiving lecture. Today we're going to be covering probability theory. But first, I want to review some of the concepts that we've been looking at in the last couple of classes. Here in front of you right now, we're going to just have a quick review of the experimental design, and then I want to have a review of sampling theory. So here for experimental design, this is actually a real scenario. So in October 2020, the New England Journal of Medicine published a paper on the use of remdesivir in the treatment of COVID-19. They conducted a double-blind, randomized, placebo-controlled trial of this drug. So you should know, that's a mouthful for sure, that's a mouthful, but you should know what that means now. Double-blind, randomized, placebo-controlled trial. If you don't know what that means, you're not quite sure, have a review of the slides from the last lecture. So this experiment was conducted. The patients were randomly assigned to receive either remdesivir or a placebo. The primary outcome was the time to recovery. So let's just go over those questions then. In this case, how many factors are there? Well, remember, a factor is the thing that's being controlled, and the only thing that's being controlled in this study is whether or not a person gets the drug or the placebo. So there's a single factor, that is the medicine, and the two levels of that factor. The first level is you get the medicine, the second level is you get a placebo. So one factor, two levels. In terms of treatments, there's also two treatments in this group. Essentially, the number of treatments is equivalent to the number of groups. Here we have one group who gets the medicine and one group who gets a placebo. So that gives us two treatments, right? So there's a group that gets the remdesivir and a group that gets the placebo. Two factors with two levels, and in this case, two treatments. What is the response variable in this case? It's just the time to recovery. Finally, the most important question: why would we be able to say that this drug causes a change in recovery time? And the primary reason is we can infer cause and effect because the subjects were randomly assigned to the two groups. So why does that matter? Let's just think about that again. The point is, we know that within any individual person, there are many factors either known or unknown, that can cause variation in their response to either taking the drug or taking a placebo. So if you have two groups of people, there's many different ways those two groups can vary from one another. They can be different from one another. So what we want to do in a design experiment, we want the only systematic difference between the two groups to be the factor that we are controlling. In this case, we want the only systematic difference to be one group is getting the drug and one group is getting the placebo. And so how do we deal with all the other sources of variation? Well, we randomize. We select patients at random and assign them to those two groups randomly. And in doing so, the hope is that any impact of all the other sources of variation will be about the same for both groups. They'll be about the same on average because we randomized. So that's the idea. So if all the other sources of variation are about the same in the two groups, and the only systematic difference between the two groups is one gets the drug and one gets the placebo, then if we see an improvement in the recovery time for the group that takes the drug, we can say the drug caused that improvement. We can actually infer cause and effect. Okay, so that's a pretty important concept and quite a deep one, in fact. Okay, so let's move on to talking a little bit about sampling theory. So here, the scenario is this. Just imagine we have a county that has 5 settlements. So we have basically 5 communities within a single county. And let's suppose 2 of those settlements are big. They contain 3,500 people each. And 3 of those settlements are quite small, only 1,000 people each. And so here's the objective. The county mayor wants to estimate the proportion of adults who plan to go away over the December vacation. And so to do so, she gets her staff to survey a random sample of 100 adults. The question is, what are the different ways that sample of 100 adults can actually be obtained. And so let's just look at the big picture. Remember that statisticians make inferences about populations by drawing a sample from that population. So in this case, the population has a population parameter P, the proportion of adults who will go away during the December vacation. The sample will give us a sample statistic P hat, which is an estimate of the population parameter. So that's the big picture. So what's the objective when we take our sample? We want our sample to be representative of the population so that we can be fairly sure that our sample statistics P hat is something close to the population parameter P. Right, so the simplest way to take a random sample is to take a simple random sample. Just think back to the case where we had 3 buckets with red, green, and blue marbles, and we wanted to estimate the proportion of each. The easiest way to take a random sample is to, if we could, we would put all the marbles into one bucket, then we would mix the marbles up, randomize them, if you will, and then take a sample of, say, 20 marbles and use that as a basis of our estimation. So here you can do kind of the same thing. If you get a list of all adults in the county, you can put that into your computer, and then you can use software to randomly select 100 of those people. And then you simply get someone to call each of those people and ask them the question, do you plan to go away in December, yes or no? So this would be a direct way of getting a simple random sample. But it's not the only way. So an alternative is to do systematic sampling. So do you remember what that's all about? Just think about that for a sec. So remember, you take one person at random. You get a list of all the people, like before, and you take one person at random. And then once you get that first randomly selected person, you go down the list, say 25 people, and pick the next one. Then go down the list another 25 and pick the next one. And you just keep doing that until you get a sample of the appropriate size. And so again, at the end, of course, you have to call all those people and ask them, yes or no, do you plan to go away in December? So that's systematic sampling, and you can see why it's called systematic. It's because apart from the first person who's selected, everyone else is selected in a sort of systematic way. But in the end, it still gives you a random sample. Cluster sampling is another choice. So there we would, remember we have 5 settlements, and so we could pick some number of settlements at random and then take a census within each. So let's say we take 2 of the settlements at random. We could take a census within each of those selected settlements. That would be cluster sampling. Multi-stage sampling is quite similar. We could, again, pick, say, 2 of the settlements at random, and instead of taking a census, we could just take a simple random sample within each of those settlements. So that's quite straightforward. Cluster sampling and multi-stage sampling have a major disadvantage, and that is that they are sensitive to unknown structure within the population. So for example, if there was one community where everybody planned to stay home in December, but another community where most people planned to go away on vacation in December, then depending on which settlement you select, your sample it isn't going to be representative of the whole population. So multi-stage sampling and cluster sampling in this scenario wouldn't necessarily be the best way. What's probably the best way, apart from taking a simple random sample, is to take a stratified sample. And so remember that we have 5 communities. The first 2 are the larger ones with 3,500 people each, and the other 3 each have 1,000. So the idea in the stratified sample is we're going to collect a simple random sample from each settlement of a size proportional to the number of adults within those settlements. So to get a sample of size 100, we could randomly select 35 people from each of the 2 larger settlements, and then randomly select 10 people from each of the 3 smaller settlements. And you can see that's going to give us 100 people in total. And then again, we would call those people and ask them, do you plan to go away or not? Right, so that's just a quick review of these different ways of collecting a sample. So as I said, today we're going to talk about the rules of probability. Just a reminder for homework, you should finish reading Module 6. That's the module that covers sampling theory and experimental design. Also, your next homework assignment is now open, or sorry, not now open, it opens tomorrow. Opens on Saturday. This is the homework covering chapters 9 and 10. And it closes, I believe, the following Friday. So you have a good week to finish that assignment. A reminder again, too, that Skill Check 5 is available on the Moodle. That is, you can think of it as a practice midterm, although I will say it doesn't necessarily cover everything you might see on the midterm. The midterm covers everything from chapters 1 to 10. In other words, anything from those chapters could appear in the actual midterm. But Skill Check 5 is a good start. It's going to cover quite a bit of the material. It's a good start for your preparation. And I will post a video solution to that skill check probably sometime today. Also a reminder that this coming Wednesday, Ray will be there to do the supplemental instruction, or whatever they call it. They call it SI. So that's going to be available. Ray knows his stuff. If you're having trouble with anything in this class, Wednesday from 1:30 to 2:30 in our classroom, Ray will be there to help you out. Lastly, just a reminder that we do have a midterm coming up again on October 23rd. So that's just over a week away. Topics will be selected from chapters 1 to 10, and I'll give you more details if I'm provided any details myself. The important thing, it's in class, so be there. It's a paper exam. Bring a calculator. You cannot use your cell phone. Okay, so now let's get into the probability theory stuff. So first, we need to define what's called a random process. This is something that's quite intuitive. Most of you are familiar with random processes. You just never called them that. So a random process is, for example, a coin toss. Why do we call a coin toss a random process? It's because you know what the outcome is. It can come up heads or tails. We call the set of all possible outcomes the sample space. So we know the sample space, it's heads or tails. But the point is, we don't know which of those outcomes will occur on any individual toss. And because of that uncertainty, we call it a random process. So, just in case you don't know what a coin looks like, there it is, heads and tails. X is a random process. We use the symbol X to represent a random variable. And here, the sample space contains two outcomes. X can be 1, representing heads, for example, and X equals 0 could represent tails. So a random variable, it's random because you never know the outcome on any individual trial. And the sample space contains all the possible outcomes. So if we look at another example, here a die toss. If you toss a die, that's also a random process. You know the die can come up 1, 2, 3, 4, 5, or 6, so that's the sample space. But on any individual toss, you don't know what's going to come up, and that's why we call it random. So here we could say X is a random variable. In this case, the sample space contains 6 outcomes. X could be 1, 2, 3, 4, 5, or 6. So you get the idea. We're taking something that's very familiar to you, flipping a coin, tossing a die, and we're sort of formalizing it mathematically because we need the formalization to build the theory of probability. Okay, so what is an event and what is its complement? In probability theory, an event is a subset of the sample space. And the complement of the event is everything else in the sample space. So for example, let's suppose we have a deck of playing cards. We draw one card at random. Let A be the event that the suit of the card is hearts. Then the complement of A is the event that the suit is something else. So it could be diamonds, clubs, or spades. So in other words, we can define an event to be some specific outcome, some specific subset of the sample space. Remember, the sample space is the set of all possible outcomes. So the event is some subset of the sample space. And the complement of the event is everything else in the sample space. Here, since we're only looking at the suit of the card that we draw, the sample space just has four things. It has hearts, diamonds, clubs, and spades. Right? So if the event is that we choose a heart, the complement is that we choose something else. So going back to the coin example, here I'm drawing a box. This box represents the sample space, which is again the set of all possible outcomes. So suppose A is the event, you get heads. We can represent that by drawing a circle in the sample space. What else is in the sample space? Well, the complement of A is that you get tails, right? If the event is you get heads, then anything else that happens is the complement, and the only other thing that can happen is you get tails. And so we call that the complement. And so you see we use a symbol, A with a C up in the corner. It's like A with a C in the exponent. The C represents, of course, the word complement. So we have A complement. The total probability inside the sample space is 1. Key idea. This is very similar to when we say the area under a normal distribution always adds up to 1. Very similar idea. Within the sample space, again, the sample space is represented by the rectangle. And the probability that something in the sample space occurs is 1. If you toss a coin, you know, heads or tails, one of those things has to happen. So the probability that some outcome occurs is 1. And so we can use that to sort of partition the probability. So suppose the probability of A, that you get heads, is 0.40 or 40%. Then we can write P of A. P of A is equal to 0.40 or 40%. Now the point is, what do you think the probability of A complement is? The total probability of all events is 1. So if the probability of A is 0.4, the probability of A complement must be 1 minus 0.4. In other words, 0.6. Right? So probability of A plus the probability of A complement adds up to 1. The total probability in the sample space is always 1. Okay, let's look at another example. Here, let's suppose the probability of A, the probability of getting heads, suppose it was 0.55. And so we write this. We say P of A is equal to 0.55, or we could also say 55%. What's the probability of A complement? Just pause the video until you have an answer to this. Okay, so I hope you paused and thought up an answer yourself. Probably most of you would say then the probability of A complement is 1 minus 0.55. It's, in other words, it's 0.45. Right. Again, the probability of A plus the probability of A complement, they have to add to 1. And so probability of A is 0.55. The probability of A complement is 1 minus that number. Okay, let's just do one more just to drive that home. Suppose the probability of A is 12%. What's the probability of A complement? So probably you would have said probability of A complement is 88%. 88% plus 12% gives us 1. Okay, so that idea I think should be clear to you now. So let's move on to something else. Let's return to the example where we have a die. So this example is a little bit more complicated. Again, the box represents the sample space, the set of all possible outcomes. So let's come up with an event. Suppose A is the event that you roll a 2, a 4, a 5, or a 6. we can represent that event by drawing a circle in the sample space. So in this case, just think for a moment, what would the complement of A be? In other words, what is left over in the sample space apart from event A? So you would have said that the complement is a 1 or a 3. So you see, putting these two events together, A and A complement, you get all possible outcomes, the whole sample space. Okay, and again, this concept that the total probability in the sample space is 1. If we suppose the probability of A is 0.67, then what's the probability of A complement? Well, the probability of A complement, that you get a 1 or a 3, is just 1 minus 0.67, which is 0.33. So you see the probability of A plus the probability of A complement add to 1. And I think what's we're doing here, we have one more of these. Let's suppose the probability of A is 0.26. What's the probability of A complement? It's 1 minus 0.26, which is 0.74. Good. So this diagram that we've been looking at all this time has a special name. It's called a Venn diagram, after, I suppose, the first person who came up with the idea of drawing such a diagram. And just to review this again, the box represents the sample space, which is the set of all possible outcomes. And so if we're drawing a Venn diagram for a coin toss, inside the box there will be heads and tails, the two possible events. If we're drawing a Venn diagram for the toss of a die, then the box will contain numbers 1 to 6, all the possible outcomes when you roll the die. A circle represents, or it doesn't have to be a circle, by the way, it could be any shape, but it's simplest to draw a circle. The circle represents an event. We can call it something, we can call it A, we can call it B, we just call it something. So here we're calling it A. It represents a subset of outcomes. The set of outcomes not in A is called A complement, and we give it the symbol A with a letter C in the exponent, the C representing complement. So if you take all the events A plus all the events A complement, you get the whole sample space. In other words, it's a partitioning of the sample space into the event of interest and then into everything else. So that is the theory of a Venn diagram. Okay, next, the probability that an event occurs plus the probability that it does not occur is always 1. This is another way of seeing exactly what we were just looking at. Because the probability that an event occurs would be the probability of A. The probability that the event doesn't occur is the probability of A complement. And so we've already seen that these two things add to 1. Now, this is a rule in probability theory, and it's quite intuitive, I believe. But usually we don't look at it this way. There's actually a different way we write this rule. So to say it another way, that's perhaps a little bit more useful. The probability that an event does occur is 1 minus the probability that it does not. And so we can write it like this. P of A is equal to 1 minus P A complement. The probability of A is equal to 1 minus the probability of A complement. And so this rule actually has a name. It's called the complement rule. So for example, it will either not rain today, let's call that event A, or it will rain today, let's call that a complement. If the probability that it will rain today is 60%, then the probability that it will not rain today is 1 minus 60%, which gives us 40. So there is the complement rule in use, in action. Okay, so moving on to the next concept. Two events are said to be disjoint if they cannot both happen at the same time. Let's look at the example of rolling a die. Question, are these events disjoint? Event A is you roll an even number. Event B, you roll a 2 or a 5. Are these events disjoint? In other words, can they both happen at the same time or not? Well, I think you'll probably see that these events are not disjoint because they can happen at the same time. You can roll an even number, which would be 2, 4, or 6. That's event A. Event B is you roll a 2 or a 5. If you roll a 2, then both event A and event B have occurred. So they can both happen at the same time, meaning they are not disjoint. So we can use a Venn diagram to visualize this. It would look like this. You see the blue is event A. The blue ellipse contains 2, 4, and 6, all the even numbers. So that's event A. The red is event B, which contains 2 and 5, and everything else in the sample space, 1 and 3, are outside those two events. And so you can see visually that these two events, indeed, they overlap, which is telling you that these events are not disjoint. Events are disjoint if in the Venn diagram the two events do not overlap, which is to say they cannot both happen at the same time. So events A and B are not disjoint in this case because they can both happen at the same time. For example, well, you can roll a 2. So suppose now the events are you roll a 1 or 2, and B is the event you roll a 3 or 4. Now the Venn diagram looks like this. You can see event A and event B no longer overlap. Because they don't overlap, we can say these events are disjoint. It's not possible for them both to happen at the same time. Right, so events A and B are disjoint because they cannot both happen at the same time. So now this brings us to a new rule. It's called the addition rule for disjoint events. It says that the probability that one or the other event occurs is the sum of the two probabilities. This applies only if the events are disjoint. And here's how we write it in symbols. We can say the probability that A or B occur is equal to the probability that A happens plus the probability that B happens. And again, A and B have to be disjoint for this rule to apply. So at this point, we need to know how to actually calculate the probability of an event. So we're going to talk about that next, and then we'll come back to this rule for this addition rule for disjoint events. So when all outcomes have equal probability, and A is any event, then the probability of A is just the number of ways event A can happen divided by the sample size. And just to be clear, what do we mean when I say all outcomes have an equal probability? If it's a coin, if it's a fair coin, that means the probability you get heads is the same as the probability you get tails. In other words, it's 50% for heads, 50% for tails. If it's a fair die, then each outcome, 1 to 6, has the same probability of occurring. So let's look at an example. So let's say event A is you roll a 6, and event B is you roll an odd number. First, I want to point out that these two events are disjoint, because if you roll a 6, you cannot roll an odd number. Likewise, if you roll an odd number, you cannot roll a 6. So these events cannot happen at the same time. They are disjoint events. So we can calculate the probability that A or B happens by adding up the probability of A plus the probability of B. So, of course, we're assuming a fair die so that we can say all outcomes are equally likely. If that is the case, then the probability of A, again, is the number of ways event A can happen divided by the size of the sample. The size of the sample space. So the probability of A that you roll a 6, there's one way you can roll a 6. And when you roll a 6-sided die, there's 6 possible outcomes. So the probability of A is 1 over 6, assuming it's a fair die. The probability of B, well, to roll an odd number, there's 3 ways you can roll an odd number. You can roll 1, 3, or 5. So there's 3 ways, and there's 6 possible outcomes. The sample space has 6 things in it. So the probability of B is 3 divided by 6. And so now, because these events are disjoint, we can say the probability of A or B happening is just the sum of the 2 probabilities. And so that's about 0.67. Okay, so I think this is another example. So suppose event A, you roll a 1, 2, or 3. Event B, you roll a 4 or a 6. Can you calculate the probability that A or B occurs? Just pause the video for a moment and do that calculation. Okay, did you pause? I hope you did. I hope you got an answer, and I hope it was this. First of all, let's remind you, in order to do this calculation, we have to assume it's a fair die so that all outcomes are equally likely. Making that assumption, if you want, you could draw a Venn diagram, and you can see from the Venn diagram alone that events A and B are disjoint. So because they're disjoint, we can use the addition rule for disjoint events, which is to say the probability that A or B occurs, it's just the probability that A occurs, which is 3 over 6, plus the probability that B occurs, 2 over 6. So in the end, you get 83% probability. Okay, let's look at another example. So consider a deck of playing cards. There are 4 suits, right? We have hearts, spades, diamonds, and clubs. Each suit contains 13 cards, and so that's 52 cards in total. So if I shuffle a deck and take a card at random, I think it should be pretty clear that every card in the deck has the same probability of being selected. And so again, we're talking about a case where all possible outcomes, all 52 possible outcomes, when you draw a single card, all those outcomes are equally likely. So let A be the event that the King of Hearts is drawn from a shuffled deck. What is the probability of A? Just take a moment, pause the video, and calculate the probability of A. Right, so every card has the same probability of being selected. The probability of an event, in the case where all outcomes are equally likely, it's just the number of ways event A can happen divided by the size of the sample space. There's only one way you can draw a King of Hearts, and there's 52 outcomes in total, and so the probability is 1 divided by 52. So it's just a little bit less than 2% probability. Okay, so let's just practice that a little bit. So I'm going to ask you some questions. What is the probability of? What you could do is pause the video with each one of these questions, do the calculation, and then resume to see if you got it right. So first, A is the event that you draw a red card from a shuffled deck. What is the probability of event A? So there's 26 red cards, 13 of them are hearts, and 13 are diamonds, out of 52 cards in total. So the probability that you draw a red card is 50%. Event B, the event that you draw a club. What is the probability when you take one card at random from a deck of cards that you draw a club? Just pause the video, do the calculation, and then resume. So the probability that you draw a club, there are 13 clubs in the deck out of 52 cards in total, and so the probability is 25%. Final example, C is the event that you draw a king or a queen. What is the probability of event C? Just pause the video, do the calculation, and then resume. So there are 4 kings in the deck, and there are 4 queens, and so there's 8 ways in total that event C can occur out of 52 events in the sample space, 52 possible outcomes. And so that turns out to be about 15% probability. Well, actually, it's exactly 15%. Okay. So on to the next concept. So remember we talked about categorical variables and contingency tables. And we could ask questions like, are these two categorical variables dependent or associated? And how would you do that? Well, if you looked at bar graphs and they look different, then you would say that they are dependent or associated. Well, here, events can also be dependent or independent. We don't use the word associated with events, but we use the words dependent or independent. So two events A and B can be dependent or independent. And the definition of dependent is this. If A and B are dependent events, are dependent events, if the knowledge that one has occurred changes the probability that the other has occurred. Otherwise, they're independent. Okay, so let's just break that down with something concrete. So let's see. Let's say event A is the event that it rained while I was walking to work. And let's suppose event B is the event that my hat is wet. So event A and event B both have probabilities. Event A has some probability based on the weather. Event B, well, my hat could be wet for a number of reasons. For example, maybe I put it in the laundry and then forgot to put it in the dryer, and so I just wore a wet hat to work. That's one way I could arrive at work with a wet hat. Another way I could arrive at work with a wet hat is it could be raining. Here's the point. There's some probability that when I get to work, my hat is wet. Sorry, let me put it this way. There's some probability that it's raining on any given day. But if I tell you I arrived at work with a wet hat, then the probability that it was raining while I was walking to work has changed. It will have gone up. It will be more likely. So in other words, the probability that it was raining while I was walking to work depends on whether or not my hat is wet when I arrive to work. If my hat is wet, that probability is going to be something higher. If my hat is dry, that probability will be something lower. So the probability that it was raining while I was walking to work, the probability that you assign to that event will change depending on whether you see my hat is wet or not. That's kind of the idea. Well, that's an example of the idea of dependency. So again, let's just look at the definition again and see if it makes more sense. So A and B are dependent if the knowledge that one of those events has occurred changes the probability that the other has occurred. And otherwise, they're called independent. Let's look at another example. So here we have two events. Event A is you draw a king. Event B is you draw a club. What is the probability that you draw a king? Well, there's 4 ways you can draw a king out of 52, and so the probability is 4 divided by 52. What is the probability you draw a king given the knowledge that the card you drew is a club? In other words, what is the probability of A given B? So if you know the card you drew is a club, now the sample space isn't 52 cards, it's only 13 cards because there's 13 clubs. And of those 13 clubs, there is exactly one king. And so knowing that you drew a club, the probability that it's also a king, there's one way that can happen, divided by 13 possibilities. And so you notice you get the exact same probability. This is telling you that the probability of A does not change when you're told that B has happened. And therefore, A and B are independent events because the probability didn't change. So knowing that B has occurred does not change the probability that A has occurred, so events A and B are independent. So let's look at a case where we have events that are dependent. And the simplest example of dependent events is when those events are disjoint. So here, event A is you draw a card and it's a queen of hearts. Event B is you draw a card and it's a spade. As you can see from the Venn diagram, these events are disjoint because they don't overlap. There's no way you can draw a queen of hearts if you draw a spade. And there's no way you can draw a spade if you draw a queen of hearts. So these events cannot occur at the same time. They are disjoint. These events are disjoint because they both cannot happen at the same time. So the probability of A, that you draw Queen of Hearts, is 1 over 52, because there's one way you can do that out of 52 possible outcomes. The probability that you draw Queen of Hearts, given that you're told the card you drew is a spade, is 0. Right? If you're told you draw a card, you don't know what it is, but you do know it's a spade, there's no way that could be a Queen of Hearts. So you can see the probability of A alone is 1 over 52. The probability of A given B is now 0. The probability of A given B has changed. The knowledge that B has happened changed the probability of A. And so these events are dependent. In general, all disjoint events are dependent. And I'm just going to give you a little heads up. Every year, somewhere on a quiz or a midterm or a final, they give you a scenario, something like this, and ask you about it, whether the events are dependent or independent. And the reason they do that is because intuitively you would think disjoint events are independent because they don't overlap. But it's just the opposite. Disjoint events are dependent. And so the reason they ask you that question every year is to see if you're paying attention. So this is something worth remembering. It's an easy point on some evaluation. Disjoint events are dependent because if one of those events has occurred, the other event is now impossible. Probability is 0. Okay, so coming to the next rule. This is called the multiplication rule for independent events. And so remember earlier we had the addition rule for disjoint events. Now we're turning to multiplication rule for independent events. So we have to first know the events are independent. If we know they're independent, we can use this rule. So if A and B are independent events, then the probability that both happen is just a product of their probabilities. And so we write the probability of A and B is the probability of A times the probability of B. Now the simplest example of this involves drawing with replacement. So suppose you draw a card from a deck, and then you make note of what it is, and then you put the card back in the deck, and then you shuffle. The reason you put the card back in the deck is we want the sample space on the second draw to be the same as it was on the first draw. That's what makes the events independent. So we draw a card at random, we note what it is, we put it back, we shuffle, and then we draw a second card. The question is, what is the probability that you get the Queen of Hearts on the first draw and you get a spade on the second draw? Well, these events are independent. The reason they're independent is because on the first draw, the probability of getting a Queen of Hearts is just 1 over 52. If you put that Queen of Hearts back in the deck and shuffle, on the second draw, the probability of Queen of Hearts is still 1 over 52. It hasn't changed. So independent events. The probability you draw a spade is 13 out of 52. And so because these events are independent, the probability that you first draw Queen of Hearts and then you draw a spade, it's just a product. So it's 1 over 52 times 13 over 52. It's about approximately 1/2 of 1%, a very small probability. And just to put a fine point on that, let's suppose for a moment that you draw the Queen of Hearts and then you set that card aside. You don't put it back in the deck. Now the sample space contains less cards. So that means on the second draw, the probability of getting a Queen of Hearts is now 0. So you see, the reason we draw a card and then put it back is what ensures the two events are independent. Drawing with replacement makes the two events independent. Okay, so finally, Let's go back to the example with the bucket with the marbles with red, blue, and green marbles. So here, suppose you make 3 draws with replacement. So you're going to take a marble at random. You're going to note its color. Then you put that marble back and then you shuffle or mix up the marbles again to randomize them again. And then you take a second draw. Put that one back, mix them up again, then take a third draw. So these events are independent because each time you take a draw, because you're putting the marble back, the proportions of red, blue, and green, those proportions do not change. So we have independent events. So the question is, what is the probability that you get green all 3 times? Well, assuming independence, it's just the probability that you get green the first time times the probability you get green the second, and times the probability you get green the third. So if we know the probability of getting green, which we do, the probability that you draw a green one is 0.45 or 45%. So the probability you get green 3 times in a row, again, drawing with replacement to give you independence, it's just a product of those 3 probabilities. In other words, the probability of getting green 3 times in a row is 0.45 cubed. That's using the multiplication rule for independent events. Last question of the day. What is the probability of the event that you get a green marble on at least 1 draw? This is a bit deceptive because this question, as it is asked, is quite difficult. If we go just back for a moment, it's easy to calculate the probability you get green 3 times in a row because there's only one way that can happen. All 3 marbles, all 3 draws have to be green. So that's very easy, a very easy calculation. If we ask you get at least 1 green marble, what does that mean? That means, well, you could draw 3 marbles and one of them is green. And there's lots of ways that can happen, right? Because the first one could be green and the second 2 could be red. The first one could be green, the second 2 could be blue. Or you could get a green, 1 blue, and 1 red. So there's several ways that can happen. And that's only if one of them is green. If both of them are green, if two of them are green, then there's a couple ways that can happen, right? You could get 2 green, 1 red, 2 green, 1 blue. And of course, all 3 could still be green. You would still satisfy the condition that at least 1 is green. So in other words, this event is, we would call that a compound event. It involves a lot of different ways that this event can happen. So it's actually quite difficult to do this calculation directly. But here's the clue. Note that the complement of A is you don't get green 3 times. In other words, none of them are green. Which means in those 3 draws, all 3 marbles are either blue or they're red. So think about it. What's the probability that a marble is blue or red? You take one at random. What's the probability of getting a blue or red one? In other words, what's the probability of not green? That probability is 31% plus 24%. So the probability that not green on the first draw is 0.55. And because you're replacing the marble, on the second draw, it's the same probability. And on the third draw, again, it's the same probability. And so the probability that not green 3 times in a row is just the probability that you don't get green on a single draw to the power of 3. And so that's about almost 17%. So this is the trickiest calculation that you're going to see in this section. So it's worth going over this, and we'll do some more review questions in class of this kind when I see you again. So I believe that was the last slide. Oh, right. I almost forgot to finish the question. The probability that none of them are green, so not green 3 times in a row, is about 16%. So the probability that at least one of them is green is 1 minus that, because we don't want the probability of A complement. We're looking for the probability of A, that at least one is green. And so, yeah, I almost forgot. The probability of A is 1 minus the probability of A complement. That's the complement rule. And so in the end, we get about 83% probability that at least one of those 3 marbles that you draw with replacement is green. Right, so let's just quickly have a very brief review. We looked at the complement rule today, the addition rule for disjoint events, the multiplication rule for independent events, and we also define what it means for 2 events to be independent. We talked about other things like sample space and what a random variable is. There's a lot of stuff packed into this one lecture, so I just would advise you to get the slides, download the slides from the Moodle. Go through these things again to reinforce your learning, because this is not particularly easy. To be honest, I think this section on probability is, I would say it's the most challenging part of the course. So put some effort into that, put some extra effort into it. Go through the notes again, maybe later today or tomorrow, well, whenever you're watching this video, sometime later, to reinforce the learning process, because again, there's a lot going on here. Apart from that, again, this is Friday, so let's see, in 3 days, the following Monday is going to be Thanksgiving, so I wish you a happy Thanksgiving, and I look forward to seeing you next week on Wednesday. Bye for now.